Hi everyone, Mr. Lee here. In this video, we're going to go over the concept of power. Now, for power, it won't take a lot of time or a lot of energy, so let's begin. So the definition of power is the following. How much work you can do in a period of time. Now, with this equation, we can actually extend this equation because work has a very specific meaning for us, right? Work is the change in energy for a system. So another way of describing power is how much energy changes for a system for a short period of time. And so from there, we can come up with our power equation. We say that power is work divided by time. Now, another way to write this is the change in energy over a very specific period of time, right? So we can write power in this fashion. And the units for power, we know that the units for energy is joules, and the units for time is seconds. Okay, so joules per second. But we don't really say joules per second for power because it just takes a little bit longer to say joules per second. So instead, we call it the watts. Watts, or a capital W for watts. Okay, now this can get a little bit confusing because work is a capital W and so is watts, but just keep in mind that if the W comes first or in the form of a formula, like we can say W is equal to 12J, right? That joules is for work, but if we were to say something like 12 watts, okay, 12 watts is power. So if the W comes after the number, they're describing the units and not the variable. All right, so we have this form of the equation for power. Now, we can also rewrite this because the definition of power is how much the energy is changing over a specific amount of time. So we could write it also like this in the form of calculus, dW dt, or the change in the work over a change in the period of time. All right, and so we would use this form of the equation if you're given a function for work. So, for example, if a object's work can be described as work for a function of time, we'll just say it's going to be like 2t squared plus 6t. Right? So if you're given a function for work for a object for a specific amount of time, and we want to find out the power, okay, because we're given the function, we got to take the derivative of this function to find the power. So let's try it. If this is the work function, if we want to find the power, we take the derivative of it. So dw dt, 2 times 2 gives us 4t. And the derivative of 6t would just give us 6. Okay, and so this would be the function for power. Okay, and we can determine how many watts is generated for a very specific amount of time period. All right, so we just went over how to go from the work function to get a power function, and we took the derivative. So let's write that down. To go from work function to a power function, we derived the work function, right? And therefore, what we can say is to go from the power function to the work function, we do the opposite of the derivative. We can integrate. We can integrate the power function. So if we integrate the power function, we will determine the work function. Okay? The two go hand in hand. We integrate the power function to get the work function. All right, so keep that in mind. And we get this from this one equation to come up with both of these. All right, now let's go over the concepts behind power, because we use power a lot in our everyday day-to-day lives. Now, power in our day-to-day lives, it's usually described as something that is strong, or we can say that it's powerful. But in terms of physics, power is just used to describe how quickly you can transform one form of energy to another, and that's where the time aspect comes in. And so if we were to think about things that have power, right? We think about cars, because cars' engines, they have this thing called horsepower. So I don't know how true the story is, but the story goes that in order to determine horsepower, okay, the story goes that they attach, so I'll do a quick little sketch, okay, they attach a little harness on the horse, and from that harness on the horse, there was a rope, and that rope was attached to a bucket, and that bucket was down a well, and they would time how long it would take the horse to raise this one bucket up from the bottom of the well with water. And that's how we came up with 1 horsepower. Okay, so horsepower is a form of power for us, but we use watts. Now, if you think about it, watts, we use watts in our day-to-day language, right? We talk about watts in terms of light bulbs. So where does that power come from that? Now, power from light bulbs is how quickly we can use that energy, and how quickly that light bulb can use that energy to turn it from this electrical form of energy into some other form, and that is the watts. So if you have different watt light bulbs, right? So what the 100-watt light bulb versus the 60-watt light bulb is describing is just how quickly you can turn that one form of energy to another form. And we see that form of energy in the form of light, and sometimes for different kinds of light bulbs, like heat is generated as well. So, you know, that's always wasted energy that gets produced. All right, so the last form of power that I can give you is a very specific and unique case. So I'm going to draw that case up here. Let's say we have an object that is being pulled to the right with a force, we call it F1, and there's a resistive force backwards, we'll call it the force of friction. Right? So in this case here, we can say that the object has a constant velocity. All right, and it's moving along the x-axis as well. So there's 2 requirements that we're talking about here. The force and the velocity are both parallel, so we can write it like this. Right? The force and the velocity are parallel to each other. That's one of the big requirements for this problem. We can actually find out how much power is being generated by that pulling force. Okay, and we can do that by actually looking at the power equation. So if we have power is equal to the work over time, and we know that work is force times the displacement, okay, also over the change in the time, we can see that force times the displacement over time. Displacement over time, that's a formula that we should be comfortable with already, and that is velocity. So what this shows us here is that force times velocity gives us power as well. Now, we can only use this if certain conditions are being met, that the force vector and the velocity vector, they are parallel, or the components are parallel, and if the object is moving with a constant velocity. Okay? So that is another form of power that you can use. All right, that's it for power. Like I promised at the beginning, didn't take much energy, and it didn't take much time, so hopefully we didn't use too much of your power. I'll see you next time. Bye-bye.